in around the same time, continuing with the whole notion of what is the charge, what are charged particles, boys were doing experiments on a gold leaf electroscope. And we had this concept of positive and negative charges. It had been around for a couple of hundred years, right back to the time of Franklin, Benjamin Franklin. So we were familiar with this concept of positive and negative charges. We were familiar with a gold leaf electroscope. We were familiar with being able to charge an object by induction. And in this case, I wanted to put the zinc on it. So there was a little phenomenon that nobody paid too much attention to called the photoelectric effect. And it was something along, it was a little puzzling, but by and large, he was figured, we'll sort this out over time. So you get a piece of zinc, throw it onto a gold leaf electroscope, charge the object negatively by induction, take this away. So I've got excess electrons on there, it is negatively charged by induction. Now here was the thing, the boys realized that probably if that's made up of electrons and electrons are going around the outside, if there's an excess of electrons there, well if you start charging, if you give that electron enough of energy, then sooner or later those electrons should leave the metal and the metal should diverge. So what they did was they shined light at the gold leaf electroscope. And they expected that, well, okay, the electrons aren't leaving right now, but you give them enough of time and eventually the electrons will leave. Because the light is coming in waves. And a little bit like, the analogy is not great, but a little bit like water waves coming in and hitting a cliff. Give it enough of time, it'll start to erode the cliff. It's more and more and more energy being absorbed. So you give it enough of time, and eventually those electrons will have to do something because they're absorbing the energy. And yet, nothing was happening. And you could, let's make this a little bit more impressive. Amy, grab that light bulb there. Aveen, grab this light bulb over here. And I'm going to grab two light bulbs over here. And we're going to pretend they're all on. This was the next thing they did. They put a bunch of, right up beside it, even if all of these guys were on, there was still nothing happening. These electrons were still moving, were still not leaving the zinc. So the question is, what was happening, all the energy that was going in? And around the 1900s, these boys could not figure it out. But they said sooner or later someone's going to explain it. Along comes Albert Einstein. Take those guys away. Take them back, please. And here was Albert Einstein, who at this stage was pretty much a nobody. Who at this stage, no Nobel Prizes, wasn't famous for anything. He was basically a patent clerk, came out of college, completely nobody. And he looks at this, something that nobody else is really looking at. And he comes up with the following idea. He does say, I'm not saying that, what I'm going to come up with, he says, is pretty, it sounds ridiculous. Because we all know light is made up of waves. So this thing should collapse over time. But he said, here's a way of looking at it that will actually explain the phenomenon. I'm not saying it's true, but until we come up with a better idea, let's go with it. And he came up with the notion that the light coming in was not made up of waves, but was made up of particles. So this was heretical, because we know it's made up of waves, we can show interference patterns. But here he is, and he says, little quote I've got from him up here, which is worth looking at. And you can imagine, like, if you're trying to if you're trying to stake a name in the world of science, what you really want to do is go with the status quo and gradually go with and get more and more respect within the organization. The last thing you want to do is come from outside, and if you are recognized as a crank straight away, well, it's going to make it almost impossible to get into the team after that. So he's really doing something very brave. He's come along and postulating the following. He's saying, imagine, this is in 1905. The body's surface layer, so he's talking about the zinc, is penetrated by energy quanta. So this is the light waves coming in, whose energy is converted at least partially into kinetic energy of the electrons. The simplest conception is that a light quantum transfers its entire energy to a single electron. So this is his famous photoelectric formula. The HF going in, this was the light quantum going in. It does two things. It releases an electron, and that's also given the symbol HF0. This is the frequency required to release an electron, plus what's left over? Kinetic energy. And that's his famous formula. So he is now gone to saying, well, we've proven that light is a wave. And he's saying, well, there ain't no other interpretation of what's going on here other than light is a particle. Can anybody come along and prove me wrong? And he left it there as a challenge. And bit by bit by bit, people have to come along and say, we can't see what's going on. We can't see any other interpretation other than what he's getting at. Right? Now that right there blows the world of physics apart. Because in around the 1900s, scientists believed, and the world at large believed, we pretty much had physics cracked. We had all the problems solved in terms of the movement of atoms. We could describe atoms in terms of protons, neutrons, and electrons. We figured we knew how everything worked. All you had to, or we knew how most things worked. It was just a case of figuring out how everything else worked by getting closer and closer and closer in terms of our investigations, by getting your accuracy to more and more decimal places. But the world of physics was going to be a closed book. And there were some scientists who deliberately were warned not to go into physics because there was nothing left to discover. And then this guy comes along and says there is something really strange at the heart of physics. Okay? So anytime you go into a bookstore and you look for popular science, it's going to be full of books that have this word quantum in the title. This is one of the more recent ones, and it just details the whole history of it. But quantum physics is one of the most fascinating because it is head-wrecking. To this day, nobody can reconcile light being made up of particles or waves. So just throw a couple of quotes at you, and then we'll move it on to the piece de resistance. This is at the very beginning. For those who are not shocked when they first come across quantum theory, cannot possibly have understood it. So if you think quantum theory is all straightforward because you've seen it in the Leaving Cert physics and you got an A in your tests, you don't know what's going on. Here is Einstein himself trying to explain to his colleagues that this thing's starting to consume his life, and he wants to say, he's looking at outside people. You know, he's up in a laboratory somewhere looking out the window. He says, looking at other scientists, and he calls them, those are the madmen who do not occupy themselves with quantum theory. He told a colleague once as they looked out a window of his office in German University in Prague. But from here, let's move it along one more time. In fact, one final quote I'll go on with here before I move it on. This is Einstein again. I thought 100 times as much about the quantum problems as I have about general relativity. Most people know Einstein because of general relativity and special relativity. But this thing is what wrecked his head. And this led into the whole nature of radioactive decay, whether it's spontaneous or whether it's not spontaneous. He could never, while he kick-started, or he was one of the guys who kick-started this, scientists eventually got to the stage where radioactivity decayed spontaneously, and we have accepted this as just part of what nature is. He could never accept that, even though he was one of the guys at the very, very beginning. Okay, we're building up to the final piece of this, and this is the following. We now know from what we did about 2 minutes ago, electrons are made up of particles. They have mass. We know what the mass of an electron is, yes? It's something by 10 to the, 10 to the minus 30 or 10 to the minus 34 kilograms. It's about 2,000 times smaller than the mass of a proton. Right. Around 1915, maybe 1920, some guy called Broglie, who was a French geezer, looked at what was happening here, and a bit like, if I make the analogy with magnetism and electricity, back in the early 1800s, a guy called Hans Ørsted was able to show that a current affected a magnetic field. Faraday came along and said, and realized the converse of that, which is that if an electric current affects a magnetic field, he was able to show that a current carrying conductor has got a magnetic effect, so one affects the other. Now, de Broglie came along and looked at this and said, we're after showing for light that light can be a particle and a wave. We're after looking at the electron, and we can show that it's a particle. And he said, I wonder, is it possible to show that all substances can be matter, or can be particles or waves? He said, I wonder, could we show that an electron, which we know to be a particle because it's got mass, we can even measure the mass of it, I wonder, can we show that to be a wave? And here's the final thing I want to demonstrate to you. That's where we're going to finish up, and this is the bit that wrecks my head. Every school in the country probably has a cathode ray tube of some description. They all demonstrate the cathode ray tube because the textbook says you must demonstrate the cathode ray tube to show the property of electrons. Let's turn this guy back on. I might plug in. We turn it on. We want the lights off for this with Julian, please. Nice and quickly. So once again, we have our green dot. And maybe I should even turn it around like this. We have our green dot as we had before. We can get it deflected in an electric or a magnetic field as we had before. If, however, we start to increase the voltage, the energy, remember the voltage dictates the energy that the electron has when it gets accelerated from here to here. Watch what happens, and particularly the front screen, you can probably see it in the back there too. So I start to increase it. If this was darker, it would be more impressive. Nevertheless, we're going to get something here that's just about observable. What do we have? Cool. Can you spot the pattern? I only spotted this by accident when I was doing it. I obviously didn't realize it was 100 years before me. You've got a series of concentric circles. This is supposed to be a mass of particles kicking in here. What could possibly cause a series of concentric circles? Interference waves. In other words, the only way to describe what's going on here, the electrons are coming through as waves and they're interfering with themselves. And here you've got, everywhere you get circles corresponds to constructive interference. So you've got constructive interference at the different layers, and in between you've got destructive interference. The only way to understand what you're seeing right there, and it's only a 10-second extension in a normal cathode ray tube, is that electrons are made of waves. But how can an electron be made of a wave if it's made of a particle? A particle is in one place in time. That's not by definition what a particle is. Waves are spread out. And in the same set of apparatus here, we can show a particle, electron is a particle, and is a wave. I think it's absolutely mind-blowing. De Broglie was a guy who, and he even looked at, you can tell the energy of the wave itself by looking at the distance between these guys. He's got the wave formula known as the diffraction, the de Broglie formula, right? And it explains the relationship between the energy of the wave and this bit here. But nevertheless, it is groundbreaking. The corollary of this, or to develop this, what they realized was just about any object which we think as being matter can be shown to have a wave, and vice versa. You can extend this the whole way up along the line. We are made up of matter. We know that if it's a matter, you can show it to be a wave. The greater the mass of the particle, the smaller the wavelength. So the bigger, so something like a proton has got a really, really tiny wavelength. Something like us has got an incredibly small wavelength. But we do have a wavelength associated with it, and you could measure it based on the mass of us. If we've got a wavelength, if we've got a wave-like pattern associated with us, there is a theoretical possibility that we could diffract. It is very, very small, but the theory says, in principle, you can diffract around the doorway, around a gap, when you go through. The gap is not of the same order as our wavelength, therefore it's not going to be likely to happen, and it's not particularly observable. But in principle, it is there. Anything that's got matter has a wave-like association, and vice versa. And I think that by itself is pretty mind-blowing. I'm done. You're done. We're done.
Yep.
Right. So what I want to do, I want to say, oh, by the way, I forgot to show you how you do actually get these leads to collapse. So let's go back and charge it again. Charging my gold leaf electroscope negatively by induction. There's an excess of electrons on there now. So what we saw was that there is no amount of visible light which will make that gold leaf electroscope, which will make the leaf deflect, which will make this neutralize. Okay? So, and that is what bothered everybody. And Einstein's idea was that it's because the photons of light coming from here weren't strong enough. What the answer to it was that if you come up with a source of light that is more energetic, so you come up with ultraviolet light, the photons of ultraviolet light do have enough energy to kick electrons off, and therefore it's going to lose its negative charge, and the leaf should deflect. So this is what happens. You come up with your ultraviolet light, shine it on it. It looks like one of the least dramatic things you're ever going to see, and yet it is one of the most profound demonstrations in the full history of physics. Because what it goes to illustrate is that the light itself must be made up of packets. There is no way to explain this phenomenon in terms of light being made up of waves. If it was made up of waves, then it means that we should just let it should work with visible light. It would just take a little bit longer. But it wasn't working at all with visible light. It only works with higher frequency light. And Einstein said not only does it have a higher frequency, it has a higher energy, and he came up with a formula that told us how much energy was in the packets of light, not the waves. He said it's made up of packets, and the amount of energy that's in a packet of light is h times the frequency. What is the frequency? Well, it's the frequency of light. So how much energy is in a packet of light? A constant called Planck's constant multiplied by the frequency of light. It doesn't get any stranger than that. And the energy, according to the formula we were looking at, the energy going in, let's say you've got 10 joules going in, it might require 8 joules to release the electron. I'm making up these figures just for illustrative purposes. It might take 8 joules to kick an electron off. The excess 2 joules are associated with the movement of the electron afterwards, the kinetic energy of the electron. If, however, this requires 8 joules for the electron to leave an atom, and the energy associated with the packet of light is less than 8 joules, then it's not going to be absorbed at all. So it's an all or nothing affair. Either you've got enough of energy to kick the electron off, in which case any excess is associated with the kinetic energy of it, or if it's not sufficient, it doesn't matter how long you leave it there, it doesn't matter how many lamps you use, it doesn't matter what the wattage in the lamp is. The wattage is just the power divided by the time. That doesn't make a difference. What makes a difference is the frequency, because the frequency tells us how much energy is associated with the photons. Okay, back to the rest of the lecture. That's it. Thank you, Peter.